When the valve of the evacuated bottle in the previous example is opened, atmospheric air rushes into it. If the atmospheric pressure is 101.325 kilopascal and zero point 0.6 meter cube of air enters into the bottle, calculate the work done by air. And they have given you the diagram of this. So they have shown you a bottle, and you can see that there is a valve, and above the valve there is a balloon sort of thing. In the previous case also we saw a bottle, and in the bottle there is a valve, and there was a balloon over it. Okay, and it was in the previous case it was helium gas. The bottle was filled with helium, and when the valve was opened, helium filled the balloon, and we found the work done in case of work done by the balloon on air. Okay, so in this case, it is the reverse of it. There is some amount of air in this balloon, and that is going to enter into this bottle once the valve is opened. Okay, so you can see that they have shown you the boundary of this bottle, and so to be precise, there is an imaginary boundary right here at the top also. So as air passes through this boundary, okay, some amount of work is being done. Okay, and let's see what it is. So in this case, there are two components. If you take the work done, you will have, because it is a closed system, the one that is in connection is the bottle and the balloon. Okay, and whatever air is inside the balloon that is going to enter into the bottle, nothing or none of the air inside this balloon is going to go into the atmosphere or anywhere else. Okay, so that is why we call it as a closed system. So if you look at for the closed system and assuming it to be a quasi-static process, we consider integral PDV. Okay, so in this case, there are two components. One is the bottle, the other one is the balloon. Okay, so we have two components here. And if you look at this, if you look at the PDV work in case of the bottle, the volume of the bottle remains the same. No matter zero point 0.6 meter cube of air is going to enter in, it is going to occupy the entire volume of the bottle. The volume of this bottle is not going to increase. இங்க இருக்கக்கூடிய காத்து 0.6 meter cube. 0.6 meter cube air in the bottle fill பண்ணாலும் it is going to occupy the same volume. இதை விட ஜாஸ்தி 25 meter cube of air in the bottle குள்ள நம்ம fill பண்ணாலும் it is going to be the same volume because it has got a rigid structure. Okay, so this volume is not going to change. So dV is still 0. So this guy, the work done in case of the bottle is 0. நான் சொல்ற புரியுதா? Whatever air from here that is going to enter in, lesser amount of air, it is also going to occupy the entire bottle. More amount of air, that is also going to occupy the entire bottle as it expands. So this guy, the change in the volume of the bottle is 0. So PDV work is 0 in case of bottle. If you take the balloon, initially the volume is 0.6 meter cube. If everything is going to enter in over here, then the final volume becomes 0. So there is a change in volume over here. And you can see if the atmospheric pressure of this particular air, so this particular air also has got this pressure. So for the first case, this entire guy is 0. For the second case, we can see it is a constant pressure process. So you know it is P times V2 minus V1. So this guy is going to be 101.325 into 10 to the power 3 for kilopascal multiplied by final volume is 0.6, initial volume is 0. So you'll get some answer. If you don't disturb this 10 to the power 3, if you're retaining it, you will get some answer in kilojoule. Okay, and you have to be a little bit careful over here. Okay, so calculate the work done by air. So this air is going to enter into this balloon. Okay, so PdV in case of bottle is 0. PdV in case of balloon. Balloon is losing its air and that is filling this bottle. So what will be the sign convention? Will it be a positive work or will it be a negative work? So the actual answer here is 60.8 kilojoules. Okay, so if it is the work done by the surrounding on the balloon, then that guy is what? Is it positive or negative? The value is 60.8 kilojoule. The work done by the surrounding on the balloon. And there is one more thing which is work done let me say by air. And what about this guy? This guy is also 60.8 and this guy is also 60.8. Which is positive, which is negative? Okay, so let me explain this with another example. Okay, I have a cylinder piston arrangement. Okay, so let me say this is state 1 when I have maximum volume. And let me say this is my state 2 when my piston moves from here to here, reducing the volume to V2. I am moving from V1 to V2. So there is a reduction in volume as we move from V1 to V2. But then that is who is doing that compression? Someone from external, some external force outside this piston that is compressing this air. Okay, so when there is a reduction in volume, I'll show you with the help of the boundary. So this was the boundary before compression, and then this part of the boundary has been reduced. Okay, so there is a reduction in boundary. There is a reduction in volume, which also means there is a reduction in the boundary of the system. Okay, so you can see that. So this is a work input case. So in a work input, you have a compression process, and during that compression process, your volume is reduced. Take the other way around. Now I am going to move from V2 to V1. Okay, so which means now the compressed gas, in case of the power stroke of an internal combustion engine, during the combustion process, once there is a spark from the spark plug, or because it is the self-ignition in case of the diesel engine, whatever may be the case, there is combustion that is taking place, and because of the high heat energy that is generated and the higher pressure, that pressure which is generated is pushing the piston in the downward direction, and there is an expansion from V2 to V1, and we call that as work output, because now work is done by the gas on the piston. In this case, in the first case, it is work done by air, by external air on the piston, or To say it other words, work done by piston on the gas inside the cylinder. That is work input. In the second scenario, work is done by the gas inside the cylinder, work done by the gas inside the cylinder on the piston. Now the gas is pushing the piston. In the first case, the piston was compressing the gas. Now the compressed gas is pushing the piston. If the piston is compressing the gas, we call it as work input because it can't compress by itself. Some external force should be given to compress the gas. So where the volume is reduced, so that is work input. When the compressed gas is pushing the piston downwards, it is giving its work to us, which is transferred to the wheels. So that is called as work output. In this case, volume is increased. Okay, hope you get it. So in case of work input, as a general sense, you can see that the volume is reduced. In case of work output, your volume is increased. In a sense, that would be an expansion process. Okay. So now here, come to this example. What happens to this balloon? Is there a volume? Is there an increase in volume or is there a reduction in volume? So in this case, it is a work input. So if it is work done by the surrounding on the balloon, that would be positive. The work done by air, the work done by air inside this balloon, that is going to be negative because as it goes out, as this air is coming out over here, the volume is shrinking. Okay, we are not talking with a reference to the bottle, we are talking with a reference to the balloon. Okay, so the work done by air in this case is negative because the boundary is shrinking or the volume is getting reduced. So whenever the volume is reduced, you can take that as work input. Okay. So this is the solution which we have seen. And this negative sign is not because of the formula. This negative sign is because of whether it is a work input or a work output process. Okay. So here there is another example, and this is also taken from PK Nath. I'll share the slides, so you need not worry. A piston and cylinder machine containing a fluid system has a steering device inside the cylinder. The piston is frictionless and it is held down against the fluid due to the atmospheric pressure of 101.325 kilopascal. The steering device is turned 10,000 revolutions with an average torque against the fluid of 1.275 Newton meter. Meanwhile, the piston of 6 meter diameter moves out by 8.8 meters. Find the net work transfer for the system. So you need to understand this. So let me depict this pictorially in the book. For a clear diagram, you can refer to the book. So here they are talking about a cylinder piston arrangement. Okay, it is containing a fluid system. Okay, so some fluid is there inside, and it has got a steering device inside the cylinder. So let's say there is a steering device over here, a stirrer. Okay, a stirrer in the form of a steering device. The piston is frictionless and it is held down against the fluid due to atmospheric pressure. So which means against the atmospheric pressure means the atmosphere is also exerting its pressure on the piston. So that is given as 101.325 kilopascal. The steering device is turned 10,000 revolutions. Okay, let's say this is a steering device, and this has been turned 10,000 revolutions, and the torque of this particular steering process, the torque that has been generated, torque is nothing but rotational force. If it is a translatory motion, we call it as force. If it is a rotational motion, then we call it as torque. Okay, so this torque is 1.275 Newton meter. The usual representation for torque is F times theta, but theta is the angular displacement. Okay, so just like you have work done is force into displacement in terms of L, force into displacement. Here you have torque in the form of um, force into theta. So here you have got the um, units in Newton meter, which is similar to work. Okay, so torque is 1.275 Newton meter. Meanwhile, the diameter of the piston. So let me say D suffix P, D for diameter. Diameter of the piston is 0.6 meter, and the piston of 0.6 diameter moves out, which means now you have to think or visualize in such a way that I am stirring this fluid, which means I am working on this fluid in such a way that I raise the energy level of this fluid, and this, because of that, this fluid is going to push the piston outwards, and that has pushed the piston by a length of about zero point 0.8 meters. Okay, it has pushed the piston about 0.8 meters. Okay, 80 centimeters, right? 0.8 meter. 0.8 meter is how much? It should be 8 decimeter, so it should be 80 centimeters, so about 80 centimeters, quite a large distance. Okay, are you able to understand the problem? So I have a cylinder piston arrangement, and here there is some sort of a fluid, and there is a stirrer, and that stirrer is rotated by some mechanism. If you look at the book, they have shown it in the form of a weight which is attached to a pulley. It can be anything. Maybe you are using a motor to stir it. That is not being given clearly, but somehow this stirrer is rotating and doing some work on the fluid. The energy level of the fluid is increased, and that fluid is pushing this piston in the opposite direction by about 0.8 meters. And now they want us to find the net work transfer for the system. Okay, so here, if you look at this particular problem, there are two work transfers here. One is the work done by the stirrer on the fluid. In the previous case, I told you, when there is a volume reduction, you call it as work input. In this case, if you think it in that way, you will find that the volume is not increasing here. The volume is not reducing here. You're just stirring, and when you are stirring, what happens? Can anyone think and tell me what happens when you stir the fluid which is inside the cylinder piston arrangement? What will happen to its
Volume increases
volume increases because of what? What
because
happens
of the
to its
stirrer.
because of the stirrer? What
It
happens to its
exerts a for it exerts a force on the piston, moving the piston outwards.
okay? What happens to the pressure and temperature when the stirrer is being rotated inside the cylinder piston arrangement? What will happen to the pressure?
Increases.
Okay, so when the pressure increases beyond the atmospheric pressure, then what happens?
Expansion.
The piston will be pushed by the fluid. Okay, uh, this is something like uh, you have two forces acting, and when one force, so in this case there is a green color force which is the force exerted by in terms of pressure by the atmospheric air, and there is another pressure which is exerted by the fluid on the piston. When this red color line, when the pressure on this side of the cylinder is greater than this pressure, then the piston will be moving towards the right. Okay, so when you're stirring, you're increasing the pressure. In another sense, we can say you're compressing the fluid. Can I say that? Maybe I am not decreasing its volume, but I am increasing its pressure, I'm increasing its temperature up to a certain point where there is no change in its volume. You should remember that gas, it occupies a larger space, and when I do work on it, I'm actually adding energy into it. Okay, so in this case, the work done by the stirrer work done by the stirrer on the fluid, what they have said is they have given you the value of the number of revolutions, and they have not very specifically said whether it is per minute or per second. So we can, as a default, we can take it as second. Okay, so that is simply 2 pi nt. If it is given as RPM, then it will be 2 pi nt divided by 60. This you would have done in your lower classes, um, which is the formula for power. Okay, so 2 pi n is the number of revolutions, and torque it is 1.275 Newton meter. So this will give you the value of the work done. Okay, and in this case it is 80 kilojoules. So this is work done by the stirrer on the fluid. So this should be taken as work input. And so this guy is negative. Okay. The second case is now this fluid is going to do some work on the piston, that is to be taken as work output. So work done by the fluid on the piston, this is equal to what if you remember, W is integral PdV. Okay, and here this formula was derived, if you remember, PW was F times DL. So this can be taken directly. So it is, this force was nothing but pressure multiplied by area into the displacement. So in this case, the pressure exerted by the fluid is given. Not by the fluid, by the atmosphere. So only when this pressure is greater than that, it will be able to move. Okay. So this guy is going to push this whatever air which is surrounding it. So that is the so this can be written in two terms. One is work done by the fluid on the piston, or you can say work done by the piston on its surroundings. You can say it in two ways. The fluid is doing work on the piston, or you can say the piston is doing work on the surrounding atmospheric air. And because this pressure is known, we do not know this pressure. Because this pressure is known, we can take this criteria, work done by the piston on its surroundings. So work done by the piston on its surroundings, that would be the pressure of the atmosphere multiplied by the area of the piston multiplied by the length traveled by the piston. So that is 101.325 into 10 to the power 3 into pi by 4, d squared is zero point 0.6 squared multiplied by 0.8. Okay, so here the value of work done by the piston on the surrounding, so that guy is 22.9. So this value over here, shall I write it with another color so that you do not confuse with the previous value? Okay, so this guy is 22.9 kilojoules. Okay, but the question is not this. They are not asking what is the work done by the stirrer or what is the work done by the piston on its surroundings. They are asking the net work transfer. Okay, so the net work transfer should be addition of this. So the net work transfer is equal to, the first guy is minus 80, the second guy is 22.9. So it is 57 point minus 57.1 kilojoule. Okay, so this is where the sign convention is important. So this is, so in this case, the work input supersedes or it is more than the work output. So such a kind of system nobody will prefer, where I am giving more input but I am getting lesser work output. So this is not an efficient system, and this is a system which brings me loss. Okay, so loss, 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 economic loss, work loss. So it is a loss. So I don't prefer this kind of system wherein I get a negative form of work. Okay, so this is the net work transfer. In the previous
When
case, I told you that whenever there is a reduction volume, you can take that as work input. Okay, if you look at this scenario, you have to visualize this problem. When you take a cylinder piston arrangement, you push the piston in the downward direction. Okay, you push this piston in the downward direction so that you compress the gas. Okay, that is in another sense, you can say that you are increasing the energy of the gas. Can I say that? Because I'm increasing its pressure, I'm increasing its temperature by compressing it. Okay, in this case, initially when the ambient pressure and the pressure inside the system, when both of them are till these two pressures are equal, in the ரெண்டு pressure equal ஆகிற வரைக்கும், you will find that the pressure here is lower than this. Okay, so now I am doing some work over here. This particular boundary remains the same. There is no increase in volume. I am doing some work, but there is no increase in volume over here till these two pressures are same, or till unto the point where this pressure becomes greater than this pressure. Okay, till that point இங்க இருக்கக்கூடிய pressure இந்த atmospheric pressureோட விட ஜாஸ்தியாகிற வரைக்கும் I am doing some work. And what happens when I do that work? அது சொல்ல முடியுமா? What happens when I do that work? Before both these pressures are equal. இப்போ இந்த சிலிண்டர் பிஸ்டன் அரேஞ்ச்மெண்ட் எடுத்துக்கோங்க. இந்த சிலிண்டர் piston arrangementல if the piston is pushed downwards, we call it as compression, right?
yes, sir.
Instead of calling it as compression, can I say that it is an attempt or it is an exercise to raise the energy of the fluid? அப்படினா சொல்லலாமா?
Yes, sir.
Because I am raising the temperature and pressure of the fluid. Okay, now come to this example. இந்த எக்ஸாம்பிள்ல வெளியில இருக்கிற atmospheric pressure விட உள்ள இருக்கக்கூடிய pressure, let's say at the initial stage, let's say it is lesser than that. Okay, or maybe equal to it. And now I am stirring this, and as I am stirring till these until the point or இங்க இருக்கக்கூடிய pressure இதை விட ஜாஸ்தி ஆகிற வரைக்கும் what happens to the fluid when I am stirring?
So the energy of the fluid increases, sir,
Energy of the
and
fluid?
it increases.
Okay. So if the energy of the fluid is increasing because of some external activity, then you call it as?
Mm. Sir, by external activity means it is called compression. So by internal activity, this is by internal activity, no, sir.
This is not internal activity. This is an external activity only, no? Your say this is connected to a motor. This is connected to a motor. When the motor rotates, the steering device is rotating. So because of this stirring, the energy of the fluid rises. So
Work
should we
input.
not call it as work input?
Yes, sir.
அடுத்த part clear இருக்கு இல்லையா? அடுத்த part வந்து the piston is doing work on the air. So obviously that is work output. So the piston is connected in a normal sense. The piston is connected to a crankshaft. Then through the power transmission mechanism, there are a lot of gears. You have got propeller shaft and so many other things. Through that, the power is supplied to the wheels. So it is obvious that the work is done by the system, by the piston is work output. அதுல பிரச்சனை இல்லையே. Or do you have problem with that also?
No, sir.
Here, a cylinder piston arrangement is shown. The piston is loaded with a mass MP. So mass of the piston is MP, that is mentioned here. The outside atmospheric pressure is P naught. A linear spring, and a single point force F1. So that is also acting over the piston. The piston traps the gas inside with a pressure P. Okay. So here, if you look at this piston, from the inside, there is a pressure which is acting, and that is pressure P. And on the outside, you will see that there is one force which is because of this atmospheric pressure P naught. There is another single point force F1, and this spring, this guy will also be uh, exerting its force on the piston. And apart from that, there is an acceleration due to gravity, and the mass of the piston itself, because of that gravitational force, it would tend to come down. So that gravitational force is also active. So if you look at the force in the upward direction, we can simply say it is the pressure which is inside the cylinder multiplied by um, the area of the piston. You okay, Ma? I'm just talking about the upward force. So the upward force is contributed by the pressure exerted by gas on the piston, and when we say it is force, it is pressure into area. So this is the pressure, and it is the area of the piston. That is the upward force. And if you look at the downward force, so let me write the entities first, and then we will balance the equation. One force is because of the pressure, atmospheric pressure P naught. The other one is because of the point force F1. The other one is because of the gravitational force. The other one is because of the spring, which has got a spring constant K. Okay. Say this, we are writing it in terms of force. So the pressure P naught exerted by the atmosphere on the piston should be multiplied by area of the piston. So this is P naught A. This is a single point force. So this is automatically in terms of Newton. So we need not touch this. and this guy is acceleration due to gravity. So what should we do? We should multiply this with
Mass.
mass. So that would give you the weight, okay? And here you have the spring constant. So if the spring is able to exert some force on the piston and push this piston down, say suppose the spring has elongated to this length, maybe pushing the piston to a lower position, the initial position of the spring, this distance can be called as x naught. And if it has pushed the piston in the downward direction, then we can, maybe this distance can be called as x. And so final position minus initial position, that is k into x minus x naught. Okay, and the unit for this spring constant, this is given as ks, so let's also take it as ks. So unit for spring constant, ks, this guy is in Newton per meter. Okay, so multiplied by meters, displacement unit for displacement is meter, that will give you Newton. And if you look at this guy, the units are, in the present scenario, the units are kilogram, and this is meter per second squared. And what is kilogram meter per second squared? That is nothing but Newton. So if we write Newton, Newton is in terms of F, F is ma. Instead of a, you have got g. So this is automatically gravitational force. So this guy is also in Newton, this guy is also in Newton, this guy is also in Newton. Now I can do a simple force balance equation where force acting in the upward direction is equal to force acting in the downward direction. So I can write this as PA equal to P naught A plus F1 plus MP times G plus Ks times X minus X naught. Okay. If I simply divide by A everywhere, I would get P naught plus F1 by A plus MPG by A plus Ks times X minus X naught by A. Now I'm going to do a simple alteration over here, wherein for the last term, I'm going to multiply and divide by area of the piston. Okay, we all know this A everywhere is area of the piston. When I multiply and divide by A, it doesn't affect the mathematical equation. So nothing is violated mathematically. So I can write this as P naught plus F1 by A plus MPG by A plus Ks times Ks divided by A squared. This guy is area, and X minus X naught, if I take it as some volume, or if I say x into A is V and x naught into A is V naught, that would become volume. X into A is length into area of the piston, so that would be the volume, which is occupied by the air when the piston is pushed downwards. V naught is the volume which is available already. So I can write this as V minus V naught by simply multiplying A with displacement. Okay, and if you look at this, assuming that the atmospheric pressure is not going to change, we all know it is 1.013 Pascal, sorry, kilopascal, 1.013 bar. So this guy is almost constant. And this is a single point acting force, and they have not mentioned it as a varying force, it is also constant. And if you look at this, the mass of the piston is not going to change. The acceleration due to gravity is not going to change. The area of the piston is not going to change. So these guys over here, these three guys can be taken as some constant C. And if you look at this Ks by A squared, the spring constant for a particular spring, that is not going to change. The name itself is constant, so Ks is a constant. Area of the piston is a constant, so that guy is also some other constant C1. And this V minus V naught is, say, some volume, and presented as a different volume. Okay, so now I get an equation P equal to C plus C1V, which is similar to Y equal to mx plus C. Mx plus C, I have written it in such a way that you can understand. So you can see that this is now a linear equation where pressure can be plotted on the y-axis and volume can be plotted on the x-axis, and C1, which is Ks by A squared, is the slope in terms of m. Okay, and this P naught plus F1 by A plus MPG by A, that happens to be the y-intercept, C. So this is a linear equation. Okay, so I can draw this So before I proceed further, let me know if you're on board with me. If there is any doubt, clarification is required, ask me. Please, quickly. Any doubts here, any clarifications needed, you can ask me. ஒண்ணு நான் தெளிவா எடுக்கிறேனா இருக்கணும், இல்லனா ஒண்ணுமே புரியலன்னு இருக்கணும். I hope it is the second one.
No doubts. No doubts.
No doubts. So I have become a genius, it seems, a master teacher, mastery in teaching. That's never going to happen, man. See, if you're not able to understand, you should open your mouth and ask me. So unless, because I don't know where you are stuck. If it is a regular class, I can gauge. But what to do? Okay, so it is why. Yeah, somebody wants to ask something, ask me quickly.
Sir,
Chalupa.
sir, how you put A divided by A in the last equation, sir?
So shall I multiply and divide by P? Does this affect this equation?
Sir, divide பண்ணோம்னா whole equation தான் sir divide பண்ணணும்.
Not necessary. Not necessary. If you look at the step very carefully, then I will write it in 2 steps then. For want of space, I wrote it in 1 step. This After this equation, now I am dividing by A. Is this okay?
Yes, sir.
Now what I am doing is, in the next step, I am not disturbing these guys. These guys I'm not going to disturb, and I'm simply going to, this A is already there. Now I'm going to multiply and divide by A, which means I can simply cancel out these two. And this doesn't violate the rest of the equation, isn't it?
Yes, sir.
Okay. So now what I do is I simply multiply and divide by A for my convenience, convert this displacement into volume. Okay. So now I can write this as P naught into plus F1 by A plus MPG by A plus Ks by A squared times X into A, distance into area is volume, minus initial distance into area is initial volume. Ipo okay ba?
Yes, sir. Now I got it.
Okay. So now after this, because these guys are all constant, we call them as a constant C, and this guy is another constant, so we call it as C1, and this V1 V minus V naught, I simply take it as some other V minus V naught. Just a minute. Sorry. Okay, so this is some volume V minus V naught. And now we are able to get an equation P equal to C plus C1V. Okay, that is another volume. So that is what is being shown here. Okay, whereas because of some constraint, I'm using the same V, but it is some other volume V. You can say this is some other volume V, which is nothing but V minus V naught. And so now I can plot a graph where P is in the y-axis and V is in the x-axis, and now it is some linear line. Okay, and I can say that maybe for the values that I have, say this is point number 1 or state point 1 for anything, for, or this can be point number 2, and this could be my P2. And if it is extended onto the y-axis, this is V1. And this guy, when extended onto the x-axis, this is V2. Okay. Now, interestingly, we know that area under the curve in a PD diagram gives you work transfer. And if you consider this by closing all the sides, this guy is a trapezium. And if you can say that this side of the trapezium has a length A, and this side of the trapezium has a length B, and this side of the trapezium has got a height h, and you can refer to some of the standard textbooks, or maybe you can Google it and you will find area of the trapezium is a plus b by 2 multiplied by h. That is the area of the trapezium. Okay, so now this area under the curve is nothing but area of a trapezium. And A in this case is B1. B, that is the height of this particular thing with reference to y-axis, that is P2. So P1 plus P2 divided by 2. And the height of the trapezium is this guy between B1 and B2, which is nothing but B2 minus P1. Okay. So when you have a problem, when you have a problem which involves a cylinder piston arrangement which is exposed to atmospheric air, and it has got a single point force, not necessarily all time, sometimes the single point force may be 0, no problem. But you have got this atmospheric pressure and this spring. Whenever you have a problem involving a spring constant, the atmospheric pressure and the gravitational force, then that becomes the relationship between pressure and volume becomes a linear equation wherein you can use this formula directly. And in gate questions or competitive exams, you will find questions from this. Not necessarily in your semester exam, but this is a problem which you may find or you will find in the competitive exams. Okay, so that is for your understanding. I have given this. Okay, so you can see that the slope of this line, that is ks by a squared. So that is being shown here. So this particular derivation or this particular concept has been taken from thermodynamics by Sontag, Klaus Bognack, and Richard E. Sontag, Fundamentals of Thermodynamics. You can refer to this textbook for many such standard problems. So we are limiting ourselves to some fundamental things, but you can refer to some standard problems if we are aiming for competitive exams. Okay, so just to give you an idea of how the complexity of the problem can be increased, I thought I can share this with the class. So this is called as Joules experiment. A very simple experiment and a very effective outcome that has been stated out of this Joules experiment. So here a container is taken, and this container is filled with some fluid. Okay, and this container is perfectly insulated. Okay, and there is a stirrer which is immersed in it, and there is a thermometer immersed in it, and apart from their insertion, everything else is perfectly insulated. Okay, now because this thermometer is there, they measure the initial temperature of this particular fluid inside the container. இது ஒரு insulated tank. இந்த insulated tank குள்ள ஒரு fluid இருக்கு. There is a stirrer. There is a thermometer. It is a perfectly insulated tank. Initial condition or the temperature is measured as T1. Okay. Now what I do is by dropping a weight, when I drop the weight, the stirrer is going to rotate. Or if I attach it to a motor, the stirrer is going to rotate, whatever may be the mechanism. Now what I do is I stir this fluid by manually or attaching it to a motor or by dropping a weight, by whatever mechanism. I'm going to stir the fluid inside this insulated tank. Maybe for 10 minutes, 15 minutes, or 30 minutes, I do the stirring. What will happen to the temperature of this fluid inside the tank? Will it be the same? Will it drop or will it be high? So when this stirring has happened, the temperature raises. Okay. So when the temperature got increased from T1 to T2, some amount of work has been done. Okay, some amount of work has been done. So if it is in the form of weight, I can see how much amount of weight has been added, and I can find out the amount of work that has been done by the stirrer. Or if it is a motor, I can estimate how much amount of electricity I have supplied, how much stirring has happened. In the previous problem, we saw what is the number of revolutions that has taken place and what is the torque. And based on that, I will be able to estimate the amount of work done by the stirrer on the fluid. So some amount of work has been done to take the system from state 1 to state 2. Okay, so this is what has happened. And it is very obvious that the temperature has raised from T1 to T2. Okay, so this was his experiment. Then what he did was, now it is in the temperature T2, he just removed the insulation. All this insulation was removed. He removed all the insulation. And now it is just a tank which is being exposed to the surrounding atmosphere. The walls of the container are exposed to the surrounding atmosphere. Now what will happen? Because this temperature is greater than the atmospheric temperature, there is a heat transfer from this fluid to the atmosphere. Okay, and they find that after a certain period of time, both of them attain equilibrium and the temperature was once again brought to T1. And from this experiment, he was able to conclude that the amount of work transfer is equal to the amount of heat transfer. The work transfer took the system from 1 to 2, and the heat transfer took the system from 2 to 1. And why do I give this convention 1 to 2 and 2 to 1? This is very important. When you look at the definition of a cycle, when you move from 1 to 2, that is a process. When you move back from 2 to 1, you are completing that cycle. You started from 1, you go back to 1. That makes it a cycle. So W1 to 2 is equal to Q2 to 1. That makes it a cyclic process. And that is why Joules said summation of Q in a cycle is equal to summation of W in a cycle. Here only one heat transfer and one work transfer is shown. You can have multiple heat transfer and multiple work transfer, but when they form a cycle, the summation of heat transfer is equal to summation of work transfer. And that can also be represented as cyclic integrals. So a cyclic integral of dq is equal to cyclic integral of dw. So in this case, the energy input was in the form of work, so that was work input, and the energy output was in the form of heat transfer, which was heat rejection, sorry, Q21. Okay, so this is what Joules experiment gave us the first law. The first law tells us that the amount of work transfer is equal to the amount of heat transfer in a cycle. That is very, very important. It is not for anything and everything. Only in a cycle, your summation of work will be equal to summation of heat. Summation of W will be equal to summation of Q. Okay, so this is a very, very important result, a very simple result, which in other words is your law of conservation of energy. Law of conservation of energy tells you that energy can neither be created nor be destroyed, but it can be transformed from one form to another form. Okay, here energy was not created, energy was not destroyed. It was first given in the form of work, and then it was transformed into another form of energy, which is heat. So this first law is nothing but uh, the law of conservation of energy in another form. Okay, so the first law tells us in a cycle, work transfer is equal to heat transfer. That's very, very important. The key word is cycle here. In a cycle, work transfer, summation of work transfer is equal to summation of heat transfer. Okay, so what if it is not a cycle but a process? Joules just stopped with the stirring process. He didn't open the insulation. If that is my case, I am doing an experiment where I have a tank, an insulated tank, and I am doing some stirring work alone. Okay, the insulation is not removed, the cycling process is not completed, but just the insulated tank is over there and just doing the stirring work. Only this part is there. Now what happens is the temperature is raised from T1 to T2. This is just a process, a heat, or I should not say heat addition, I should say it's a work input, a process involving a work input. Here only a process has taken place where some amount of work has been, some amount of energy has been added to this fluid. How do I represent this? Okay, so in that case, what has happened is I have done some work, and that work has raised the energy level of the fluid. I have done some work, and that work has raised the energy content or the energy level of this particular fluid. Okay, so to represent that, we use something called Q equal to delta E plus W. Okay, and this is what we have for a process. So in this case, there is no heat addition. The insulated tank insulation, because of the insulation, heat transfer is 0, which means W equal to minus delta E, or delta E is equal to minus W. And for our case, this is correct because work input, we represent it as minus W, work input as negative. So this negative work input has raised the energy level of the fluid. Okay, so this is the first law for a process. So in other words, in a general sense, we can say Q equal to delta E plus W. Okay, so that is what we have when the first law is applied to a system undergoing a change of state. Undergoing a change of state, the change of state happens only in a process. Okay, so first law applied to a system undergoing a process, Q is delta E plus W. Okay, and this delta E is with the reference to the energy balance. Whatever energy that you are giving in, that should be equal to the energy that is going out plus the energy that is being stored. If you take this example wherein we have seen the energy in is equal to energy out plus energy stored. If you look at this example, you are giving energy in the form of work input. So that is your E in, which is work input. There is no work energy out of the system because this particular tank is perfectly insulated. There is no other work which is done by the gas to the surroundings, which is crossing the boundary. So there is no energy out. But you can see that this energy is stored. You have raised the temperature of this particular fluid, which means you're raising the energy content of the fluid, which is stored inside the system. And it is this energy stored when you are removing the insulation, this energy stored is liberated to the surroundings in the form of heat rejection. Okay, so this is your simple energy balance. So if it is a cycle, if it is a cycle, summation of Q is equal to summation of W, and the summation is for a cycle. If it is a process, then Q equal to delta E plus W. And what is this E? We call it as, generally we call it as energy. And for a thermodynamic closed system, we will call it as delta U, and this U will be called delta U will be called as internal energy, and delta will be called as change in internal energy. And this is very, very important here. What if you write this as E plus W? Why not E plus W? Why do we give Q equal to delta E plus W? And I say that this equation here is absolutely wrong, and this equation is only correct. So why do I say the first equation is wrong, and why do I say that the second equation is right? The first equation doesn't have a delta. The second equation has got a delta. What is the significance of this delta? Can anyone tell me, or does anyone know? If anyone knows, you can tell me. Why do we have this delta E instead of E? Okay, I'll tell you.
So it's the change in internal energy, sir.
Yeah, it's change in internal energy. Why should we call it as change in internal energy? That is my question. I didn't say change in heat. I didn't say change in work. I didn't say change in heat. Delta Q is equal to delta E plus delta W. I didn't say delta Q. I didn't say delta W. Why do I use delta E alone? Why not E plus W? This is very, very important, because if you take any substance, anything for that matter, you can take anything, maybe a small leaf, or maybe a piece of chair, a small piece of plastic, anything that you take, any object that you take, okay? If you take that particular object, in that object you have got molecules. Take a single molecule of it. It has got atoms in it. Take a single atom. You have got something in that atom called a nucleus. And inside that nucleus, you have something called neutrons. You have something called proton. And if you are able to break that nucleus, what do you get? You get large amount of energy. So what does that tell you? Any substance, anything that you have has got some amount of inherent energy inside it. And we call that as internal energy. You have so many things for that, which we'll be seeing later on, maybe in a couple of slides. You have got something called translational energy, rotational energy, vibrational energy, electromagnetic energy. There are so many forms of energy for one single electron or one single atom. So that, putting all that together, you call it as internal energy. And you know, when I had this initial condition, when this particular fluid was at the initial temperature T1, it already had some energy E1. When I did some stirring work over it, the energy level increased and it became E2. And because of that, the change in energy was E2 minus E1. You can't say that initially the energy was zero. No, you can't say that. everything, anything in nature, anything, even a small piece of sand, a single, um, what do you say, a single particle of sand, it has got a lot of energy. But if you can break that nucleus, that is enormous energy, capable of destroying a city. Okay, so that is why you can't say that energy is zero. So we call it as delta E. If you take heat, initially there was no heat supplied over here. Initially heat supplied is zero. When heat is leaving the system, we estimate it in the form of heat. Before the stirring work was happening, there was no work done on the system. Work done was zero. After the stirring work, I say some amount of work has been done by the stirrer on the fluid. So it is work input. Can you differentiate this? Work done and heat transfer, they can be zero. But energy, it cannot be zero. Everything in it has got some inherent energy. Okay? So that is why you can't say E. So none of you should ever write Q is equal to E plus W. Absolutely wrong. It should be Q equal to delta E plus W. Because anything and everything in nature has got inherent energy or internal energy in itself before heat or work is done on it or by it, whether heat is entering it or leaving it, work is done on it or by it. Are you able to understand this? So it should be always Q is equal to delta E plus W. So whenever, or in a later sense, we will be calling it as Q equal to delta U plus W. So in thermodynamics, we will not be able to measure the energy of a particular thing. You can't measure energy. If you are able to measure energy, you will be a famous scientist like Einstein or Newton. So far, 2021 years, before and after, so almost 4,000 to 5,000 years as per the calendar that we have, for about 4,021 years, no one is able to measure energy. But we are able to measure the change in energy. Okay, so you should be always very clear about this delta. Don't miss this delta. If you miss this delta, then what you're writing is wrong. So in thermodynamics, we will be always talking about delta E, delta U. In none of the equations you will find E. Maybe for mathematical purposes, sometimes we write it as E, but technically or as a physical significance, there is nothing that you can call as E. It is only delta E that we can measure. Okay, so when it is a process, we always write it as Q equal to delta E plus W as a general scenario. Okay, so for a closed system, we will be writing it as Q equal to delta E plus W. Why? I'll say that in a couple of slides later on. So I have given the space, I forgot that. Okay. So now we have seen this term delta E. So Q equal to delta E plus W. And from our previous discussions, we know that this guy over here, heat transfer, this guy is a path function, and this guy, work transfer, is also a path function, which means it is dependent on path. What about this guy? Is this guy a path function or a point function? So we know that because these two guys, Q and W, are path functions, they are not properties. We know that. Okay. When we discuss about properties, we said they should be independent of path. Because these two guys are path functions, they are dependent on path, they are not properties, they are not thermodynamic properties. So now the question arises, what about this guy delta E, whether he is a property or it's not a property, whether it is a point function or a path function. So let's see, let's check this. So let me take a PV diagram. and I have state points 1 and 2. So I have, say, I am taking a path A to move from 1 to 2, and I am taking path B to move from 2 to 1. I am taking path C also to move from 2 to 1. Is that clear? For moving from 1 to 2, I am taking a path A. For moving from 2 to 1, I am taking two paths. One is path B, the other one is path C. Okay, so now I have got two cycles. One is a cycle which is 1 to 1 following the path AB. The other one is a cycle 1 to 1 following the path AC. Is that clear? One is a cycle 1 to 1 which is following path AB. The other one is 1 to 1 which is following the path AC. If you take this guy, say for moving from 1 to 2, I can say, applying the first law, QA equal to delta EA plus WA, right? And for moving from 2 to 1, I can write QB equal to delta EB plus WB, right? Now, 1 to 1 is a cycle. So what does that mean? Summation of Q over the cycle should be equal to summation of W over the cycle. Is that not? So there is no harm in adding QA plus QB, which is equal to WA plus WB. Okay, up to this clear? Now what I do is, from this equation, I write this as QA. I'm just bringing WA to the right hand side minus WA equal to WB minus QB, or I will write this as minus of QB minus WB. Any doubts up to this? If you have doubts, if you're not able to follow, if I'm very fast, please let me know. Can I proceed? One of you respond?
Yeah.
Yes, sir.
Okay. So if you look at this equation, the first equation, this guy, QA equal to delta EA plus WA, if I rearrange this becomes QA minus WA is equal to delta EA, which means I can write this guy as delta EA. Similarly, for this equation, if I bring WB on the right hand side, QB minus WB is delta EB. So I have got QB minus WB, which is minus delta EB. Look at this result. Delta EA is equal to minus delta EB. Let's take this as equation 1. Okay. So this is for a cycle which was following the path AB. Okay. Now let's consider the cycle 1 to 1, which is following the path AC. Let me follow the same steps. For moving from 1 to 2, using the path A, I can write QA equal to delta EA plus WA. Let's leave some gap. for moving from 2 to 1. Now it is following the path C. So QC is delta EC plus WC. Okay. Now applying the first law, because it is a cycle, applying first law to the cycle 1 to 1, following path AC. Now I can write this as QA plus QC is equal to WA plus WC, or I can rewrite this as QA minus WA equal to QC minus WC, or minus of, sorry, this should be WC minus QC. WC minus QC, which is minus of QC minus WC. Just like we did in the previous case, we can say QA minus WA is delta EA, and this guy QC minus WC is delta EC. So this is delta EA on the left hand side, and this guy is minus delta EC, which is on the right hand side. So now compare equations 1 and 2. The left hand sides are equal. Both of them are delta EA, which means the right hand side should be equal, which means minus delta EB equal to minus delta EC, or I can simply say, I can cancel out this minus term and simply write this as delta EB equal to delta EC. What do you understand from this? What do you understand from this? What do you understand when I say delta EB is equal to delta EC? நீ பேசலன்னா 1:30 வரைக்கும் கிளாஸ் எடுத்துட்டே இருப்பேன். எனக்கு அடுத்த கிளாஸ் 1:30 தான்.
Sir, both the cycles are cancelled.
Both the cycles are
In same path.
No, it is not. In one cycle, I am taking path A and path B. The other cycle, I am taking path A and path C. What I am trying to tell you here is, see, I am taking two different paths B and C, but when I look at the change in internal energy, whether I am taking path B or path C, the internal energy, the change in internal energy or the change in energy is still the same. You take path B, there also you will find the same change in energy. So the change in energy is not path dependent. So this guy delta E, this guy is not path dependent, which means this guy is not a path function but a point function. It is dependent only on the points 1 and 2. The path B and path C, it is dependent on 1 and 2 only. It is not dependent on path B or path C. Irrespective of path B or path C, it is the same internal energy. If you take E, A and B, there is a reversal in path, so you find there is a negative sign. So there is a change in internal energy here. But when you look at these two paths where they are moving from 2 to 1, in this case, this guy is moving from 1 to 2, and this guy is moving from 2 to 1. That is the path A, and this is the path B. So in this case, they are taking two different paths, and so there is a change. But here, they are moving from 2 to 1. They are moving to the same state points. From 2 to 1, they are traveling. Here, this guy is traveling from 1 to 2. This guy is traveling from 2 to 1. This guy is traveling from 2 to 1, and this guy is also traveling from 2 to 1. Now, you find that the change in energy is the same. So this is a point function and not a path function, and that is why we call change in energy is a property. Just like your pressure, volume, temperature is a property, your change in energy is also a property of a system. And therefore, you can say cyclic integral of dE is equal to 0. In the previous case, in the first law, what we saw was cyclic integral of dQ is equal to cyclic integral of dW. Okay? Never, never, ever we will say cyclic integral of dQ is equal to 0. Absolutely wrong. Because this guy is path dependent. Okay? So you won't have cyclic integral of dQ equal to 0. Neither will you have cyclic integral of dW equal to 0. No, it is not equal to 0. But cyclic integral of dE is equal to 0 because you can find delta EA. Sorry, there is a small error over here. This should be delta EA is equal to minus delta EB. And here delta EA should be minus delta EC. Sorry about that. There is an error here in the derivation. And whatever I have done here, that is correct. Okay. So that is why you will find that change in energy is a property. Okay.